Using mesh analysis, find the power delivered by the dependent source in this circuit. First, let's label the mesh currents, IA and IB. Always use the clockwise direction. Trust me, it helps. For mesh A, let's write the KVL equation. We have negative 100 volts from the source plus 5 times IA, that's the voltage drop across the 5 ohm resistor, and then the 50 ohm resistor is common to both meshes. When a resistor is common to 2 or more meshes, multiply its resistance by the difference of currents. And the difference always goes like this: your mesh minus other meshes. In this case, this will be 50 times IA minus IB. We're done, so this must be equal to 0. Let's divide everything by 5 and take the constant to the other side. We can expand the pair of brackets and group like terms. So that's it. This is the first equation involving IA and IB. And now we can turn our attention to the second mesh. We have positive 150 IX. Now we have a 20 ohm resistor and a 30 ohm resistor in series, so this will be 50 times IB. And again, the 50 ohm resistor hanging in the middle is common to both meshes. Remember, your mesh minus other meshes. So 50 times IB minus IA this time. We're done, so this must be equal to 0. Divide everything by 50, group like terms, and now we see a problem because the equation involves IX when we only want it to involve IA and IB. So we have to express IX in terms of the two mesh currents. In order to do that, let's zoom in and have a look. What is IX in terms of IA and IB? We can see that IX is labeled as the current flowing upwards through this middle 50 ohm resistor. Which of the two mesh currents is flowing up? Take a moment, and I'm sure you can agree with me that IB is the current flowing up. Trace the clockwise direction and you can easily see it for yourself. IA, however, is flowing down through the 50 ohm resistor. This must mean that IX is IB, the current that agrees with it, minus IA, the current that opposes it. So, replacing IX by IB minus IA and expanding, we can then group like terms and the equation will end up being negative 4IA plus 5IB equals 0. An easy system of two equations with two unknowns, giving us IA equals 20 over 3 amperes and IB equals 16 over 3 amperes. And now we're ready to find the power delivered by the dependent source. In general, we have three equations for power: voltage times current, the square of the voltage divided by resistance, and the square of current multiplied by the resistance. When you want to find the power associated with a source, you can only use the first equation because you don't know the resistance of a source. So you should always multiply voltage by current. This will give us the power delivered by this 150 IX dependent source. What is the voltage? Its rating, 150 IX. What is the current? It's IB. And we don't need to attach a negative sign here because IB is entering the positive terminal of the dependent source. Okay, IB is 16/3, and remember IX is IB minus IA. The fractions have a common denominator. We can take 3 outside the brackets. 150 over 3 is 50. 16 minus 20 is negative 4. 50 times negative 4 is negative 200. And finally, negative 200 times 16 is negative 3200. So the power is around negative 1067 watts. It's negative as expected because the problem is telling us that this source is delivering power to the network, not absorbing power. So the conclusion is that the dependent source is delivering approximately 1 kilowatt of power to the circuit.